We now discuss about integrals that involve powers of trigonometric functions. If we have integrals of the form, say, sine cube theta d theta, or the integral of tangent to the p of theta d theta, or the integral of cosecant cube theta cotangent cube theta d theta, we cannot immediately apply the generalized power formula. Huh? We might be tempted to use the generalized power formula, but we should realize that eventually we'll not be able to come up with an answer. So, for example, for sine cube theta d theta, we can take u as sine theta. We then check the differential du, and that is equal to cosine theta d theta. Going back to the integral, the complete du is supposed to be cosine theta d theta, and we cannot just introduce cosine theta in the integrand and pre-multiply it by its reciprocal. We are not allowed to do that. We can only introduce a constant in the integrand and pre-multiply it by its reciprocal, but not for a variable or a function. The same thing goes for tangent to the fifth theta d theta and cosecant cube theta cotangent cube theta d theta. We cannot, as of the moment, use the generalized power formula. What we are going to do is we will set up our integrand in such a way that we'll come up with an expression that can be integrated using any of the fundamental integration formulas. So for powers of trigonometric functions, we will be grouping these types of integrals into powers of sine and cosine, and the other set of powers of trigonometric functions are powers of the other four trigonometric functions: tangent, cotangent, secant, and cosecant. And for each of these groups of integrals, we will consider four types or four cases. So there will be four cases each for each group of integrals. We now consider the first set of four cases involving powers of sine and cosine. For case 1, we have integrals of the form sine to the mu du or cosine to the mu du, where the exponent m is a positive odd integer. Example, sine cube 4x or cosine to the fifth 3y. The exponent is a positive odd integer. And what is the rule? If we have a factor of sine, we shall factor sine u or sine 4x. And the remaining factor will be expressed in terms of the complementary function cosine. If we have a power of cosine, we will factor cosine, and the remaining factor will be expressed in terms of sine. For any of these two cases, we will be using the fundamental trigonometric identity sine squared u plus cosine squared u equal to 1. So again, for powers of sine and cosine, where the exponent is a positive odd integer, we will factor sine or cosine, and the remaining factor will be expressed in terms of its complementary function using the identity sine squared u plus cosine squared u equal to 1. Remember that sine and cosine are two trigonometric functions that are compatible to each other. Why? because the derivative of sine is cosine and the derivative of cosine is negative sine. Alright? So we'll see its use in the succeeding examples. Let us now try and evaluate the integral of sine cube 4x dx. So in here, we see that the exponent of sine is 3, a positive odd integer. So what is the rule? We shall factor sine 4x. So we will write sine cube 4x as sine squared 4x and sine 4x dx. The factor sine squared 4x will now be expressed in terms of cosine using the identity sine squared 4x plus cosine squared 4x equal to 1. No? So the identity is sine squared 4x plus cosine squared 4x equal to 1. Sine squared 4x is 1 minus cosine squared 4x times sine of 4x dx. We then split this into two integrals. Sine 4x dx minus the integral of cosine squared 4x sine of 4x dx. For the first integral, it takes the form sine u du. We only have to introduce the constant 4 so that we can complete the differential of 4x, which is 4 dx, and multiply it by 1/4. So the integral of sine u du is negative cosine of u. 1/4 negative cosine of u, which is 4x. Minus. For the second integral, we see a power of cosine. We see a power of cosine together with the function sine. So we shall apply here the generalized power formula. Our u is cosine 4x. For the generalized power formula, it is of the form u to the n du. So our u is cosine 4x and our du is negative 4 sine of 4x dx. So what we have is sine 4x dx and we introduce negative 4 to complete our du. So we multiply by the reciprocal negative 1/4. So negative of negative 1/4 is positive 1/4 and u squared du becomes u cubed. But our u is cosine 4x to the power of 3 over 3 plus c. So negative 1/4 cosine of 4x plus 1 over 12 cosine cube 4x plus c. We can simplify this by factoring 1 over 12 cosine of 4x. So let us begin with the positive term. 112 cosine cube 4x. We factor 112 cosine 4x. That will be cosine squared 4x. Minus 12 divided by 4. That will be 3. And we factored cosine 4x plus c. So that is our final answer. Next problem, we integrate x cosine raised to 5 x squared dx. Again, we examine the exponent 5, which is a positive odd integer. So we apply the rule. We shall write cosine raised to 5x squared as cosine to the 4th times cosine. So we retain x, cosine raised to 4, x squared and cosine x squared dx. Cosine to the fourth x squared, that is equivalent to cosine x squared or cosine squared x squared quantity squared. So x cosine to the fourth is cosine squared and cosine squared is 1 minus sine squared x squared quantity squared. No? Cosine squared x squared is 1 minus sine squared x squared. Everything to the power of 2. Then cosine of x squared dx. For this part, we expand. So x 1 minus 2 sine squared x squared plus sine to the fourth x squared quantity times cosine x squared dx. We then write this as a sum of three integrals. Integral of x cosine x squared dx. We distribute our x. And then, same thing with cosine x squared. So, minus 2 integral of x sine squared x squared cosine x squared dx plus the integral of sine to the fourth x squared cosine x squared dx. We continue. For the first integral, we shall apply here cosine u du. Our u is x squared and its differential is 2x dx. So we complete by multiplying x dx by 2 and per-multiplying it by 1/2. So 1/2 integral of cosine u is sine of u or sine x squared. Okay? There. Minus 2. How about x sine squared x squared cosine x squared dx? We see that we have here a power. No? We have a power involving sine x squared. So it shall take the form u squared. Takes the form u squared, where your u is sine x squared. Alright? So our u is sine x squared. And du is 2x cosine x squared dx. X cosine x squared dx, it lacks 2, and we multiply it by 1/2. Alright? So negative 2 times 1/2 and apply the generalized power formula. U squared becomes u cubed or sine cube x squared over 3. Plus, for the last integral, for this integral, we have the same u and du. It lacks the constant 2 and we multiply by 1/2. So plus 1/2 and sine raised to 4 becomes sine raised to 5 x squared over 5 plus c. 1/2 sine of x squared minus, the 2 will cancel, 1/3 sine cube x squared plus 1/2 times 1/5 is 1/10 sine to the 5th x squared plus c. And so that is our final answer. We proceed to the second type of integrals involving powers of sine and cosine. We have the integral of sine to the nu du or cosine to the nu du, where the exponent n is a positive even integer. So for case 1, the exponent is odd. For case 2, the exponent of sine or cosine is positive even integer. And what is the rule? We immediately apply the identity, the corresponding identity, sine squared u equal to 1/2 quantity 1 minus cosine 2u, and cosine squared u equal to 1/2 the quantity 1 plus cosine 2u. Now, these are the half angle formulas. No? We know that sine squared of x over 2 is 1/2 1 minus cosine of x. And cosine squared x over 2 is 1/2 1 plus cosine x. Alright? So these two are actually similar. These are similar identities. So what do we see in our identities? There is a reduction in the exponent from 2 to 1. And the angle u becomes 2u. So, reduction of the power to 1 will make the argument u twice, will make the argument u converted to twice the argument or 2u. Okay, so one is negative and the other one is positive. Let us now take on the next example. We work on the integral of e to the x cosine squared e to the x dx. Clearly, the exponent of cosine is a positive even integer. So we shall apply immediately the identity corresponding to cosine squared. So we first write e to the x. And cosine squared is 1/2 the quantity 1 plus cosine of, what do we do with the argument e to the x? We double e to the x, so we write 2e to the x dx. We can write the constant 1/2 before the integral sign, and then we distribute e to the x. E to the x plus e to the x cosine 2e to the x everything dx. We can also split this into two integrals. 1/2 the integral of e to the x dx plus 1/2 the integral of e to the x cosine of 2e to the x dx. The first integral involves exponential function e to the u. So e to the u du is e to the u 1/2 e to the x plus 1/2. We then apply cosine u du to the second integral, where your u is 2e to the x and du is 2e to the x dx. So e to the x dx is your du except for the missing constant 2. So multiply it by 2 and then 1/2. So 1/2 times 1/2, and the integral of cosine u is sine of u, or sine of 2e to the x plus c. So our final answer is 1/2 e to the x plus 1/4 sine of 2e raised to x plus c. Okay? So we go to the next example for case 2. Let us evaluate the integral of sine raised to 4 2t. So the exponent is 4 Again, it is a positive even integer. So the rule is to apply the identity for sine squared. No? Sine raised to 4 2t is the same as sine squared 2t squared. So for sine squared, it will be 1/2 quantity 1 minus cosine of twice the angle 4t. But everything raised to the power of 2 dt. Okay? 1/2 of the quantity 1 minus cosine 4t is good only for sine squared. Our integrand is sine raised to 4. So we have to square the entire term. Then we write the constant before the integral. 1/2 squared, that is 1/4 integral of. For 1 minus cosine 4t, quantity squared in the expanded form is 1 minus 2 cosine of 4t plus cosine squared of 4t dt. Continuing, we have 1/4. We can integrate the first one, dt, and the integral of dt is t. There. Minus 2. How about the integral of cosine 4t? The integral of cosine is sine of 4t times 1/4. Why 1/4? Because of the derivative of 4t, which is 4. So the differential is 4 dt. That is why 1/4 figures out in the answer. Then plus cosine squared 4t. Take note, the power of cosine is positive even integer. So we cannot integrate it yet. We apply the identity for cosine squared, which is 1/2 quantity 1 plus cosine of twice the angle 4t, that is 8t dt. So 1/4 quantity t minus 2 over 4 is 1/2 sine of 4t plus 1/2. We integrate these two, dt and cosine 80 dt. So for the integral of dt, that is t, plus the integral of cosine is sine of 8t times 1/8 because of the derivative of 8t, plus the constant c. So let us simplify this. 1/4 quantity, we have here t and 1/2 of t. So t and 1/2 of t, that is supposed to be 3/2 t minus 1/2 of sine 4t plus 1/2 times 1/8 is 1 over 16 sine of 8t plus c. If you want to get rid of the fractions inside, we can factor 1 over 16. So 1/4 times 1 over 16 is 1 over 64. So 16 divided by 2 is 8 times 3 is 24t minus 16 divided by 2 is 8 sine of 4t plus sine of 8t plus c. Okay, so that concludes case 2. So recap, for case 1, powers of sine or cosine are positive odd. For case 2, powers are positive even. What is the rule? For case 1, we shall factor sine or cosine and apply the identity sine squared plus cosine squared equal to 1. For case 2, powers of sine or cosine are even. We apply the identities sine squared and cosine squared equal to 1/2 the quantity of 1 plus minus cosine of twice the angle 2u. Alright? We now proceed to case 3, wherein the integral is of the form sine to the mu cosine to the nu du. Take note that sine and cosine appear together in the integrand with powers m and n. If one of the powers or both powers are positive odd integers, we will apply the same rule as in case 1. Meaning, for the factor that has an odd exponent, we shall factor sine or cosine, and all the rest, all the other remaining factors must be expressed in terms of the complementary function. Right? So, in the event that both m and n are positive odd integers, it is advisable to apply the rule to the one which has the lower exponent. Say for example, sine raised to 3 2t and cosine raised to 7 2t. Both exponents are positive odd integers. It is advisable to apply the rule to sine cube 2t. You can apply the rule to cosine raised to 7, but it will take a longer computations to arrive at an answer. Whereas if we apply the rule to sine cube, 3 being the smaller between 3 and 7, we'll be able to determine the integral in a much shorter way. So we apply the same identity, sine squared u plus cosine squared u equal to 1. So for the integral of sine cube 5y over cosine squared 5y dy, first step is to rewrite this as sine cube 5y cosine raised to negative 2 5y dy. Instead of using the reciprocal function of cosine, which is secant, we will simply write 1 over cosine squared as cosine raised to negative 2. Because if we will introduce a secant function, sine and secant are not quite compatible to each other. No? So we write 1 over cosine squared as cosine to the negative 2. And see that the exponent of sine is a positive odd integer, so we will apply the rule to sine cube 5y. And we shall factor sine 5y. Thus, we have sine squared 5y, cosine to the negative 2 5y, sine of 5y dy. Alright? All the rest must be in terms of the complementary function of sine. And the complement of sine is cosine. So there's nothing else, there's nothing that we will do to cosine to the negative 2 5y, no? Because that is already the complementary of sine. It is sine squared y that we are going to express in terms of cosine. And that is equivalent to 1 minus cosine squared 5y. So sine squared 5y is 1 minus cosine squared 5y times cosine to the negative 2 5y sine of 5y dy, which is equal to the integral of, we shall distribute this to 1 and cosine squared. So first integral is cosine to the negative 2 5y sine of 5y dy minus, what will happen to cosine squared times cosine to the negative 2? The product is cosine raised to 0. And we know that that is equal to 1. So times sine of 5y dy. For the first integral, we can apply the generalized power formula, where u is cosine of 5y and du is negative 5 sine of 5y dy. So we already have sine 5y dy, it only lacks negative 5. We multiply it also by the reciprocal, negative 1/5. And applying the power formula, our answer will be negative 1/5. Cosine raised to negative 2 will become cosine raised to negative 1. Negative 2 plus 1 is negative 1 over negative 1. Minus. For sine 5y dy, obviously, you will be using here sine u du. And the integral of sine u du is negative cosine of 5y. But because of 5y, the differential is 5 dy, so we introduce 5 and multiply it by 1/5 plus c. Okay? So the integral of sine is negative cosine. And because of 5y, we multiply it by 1/5. So negative 1/5 over negative 1 is positive 1/5. And cosine raised to negative 1 is 1 over cosine. No? This is 1 over cosine. And 1 over cosine is, of course, equal to secant 5y. Then negative and negative 1/5 is positive 1/5 cosine of 5y. So we shall factor 1/5 plus c there. As a second example for case 3, let us evaluate the integral of cosine cube ln of x, square root of sine of ln of x all over x dx. Let me rewrite this as the integral of cosine cube of ln x, and sine, square root of sine ln x is sine raised to 1/2 of ln x dx all over x. Then apply the rule to cosine cube. No? Apply the rule to cosine cube. So we shall now write this as cosine squared of ln x sine raised to 1/2 of ln x, the other factor cosine ln x dx over x. So we preserve cosine of ln x dx over x. All the rest must be in terms of sine. So you already have sine 1/2. For cosine squared, it becomes 1 minus sine squared. So cosine squared becomes 1 minus sine squared of ln x times sine to the 1/2 of ln x cosine of ln x dx over x. We shall now multiply this or distribute this to 1 and sine squared. So let me use a black ink. Integral of sine raised to 1/2 of ln x cosine of ln x dx over x minus the integral of sine squared and sine to the 1/2. So we need to add 2 and 1/2. That will be 5/2 of ln x times cosine of ln x dx over x. For both integrals, we will be using the generalized power formula. Okay? Where your u is sine of ln x. Sine is your u. And your du is derivative of sine is cosine of ln x. Derivative of ln x is 1 over x times the differential dx. So that is our du. And we see that for both integrals, you have the complete du. You have the complete du. So you can apply immediately the power formula. The power formula, u to the 1/2 du, which is u raised to 3 halves, or sine raised to 3 halves of ln x over 3 halves, minus 5 halves, that is your n. So sine raised to 5 halves plus 1 is 7 halves ln x over 7 halves plus c. Let me factor 2 over 21 and sine to the 3 halves of ln x. So factoring 2 over 21 from 2/3, that will be 21 divided by 3, 7. Now we factored sine to the 3 halves, minus, we factored 2, 21 over 7 is 3. Sine to the 7 halves, take away 3 halves from 7 halves, that will be 4 halves. So sine to the 4 halves, or 2, of ln x plus the constant c. There. We are now down to the last case for powers of sine and cosine. Now, case 4 is actually a generalization of case 2. Just like case 3, case 3 is a generalization of case 1. The rule applied to case 3 is the same as the one used for case 1, where the power of sine or cosine is a positive odd integer. Now for case 4, which is similar to case 2, both powers of sine and cosine are positive even integers. Just like what we did for case 2, we will apply the trigonometric identity sine squared u equal to 1/2 of the quantity 1 minus cosine 2u, and cosine squared u is equal to 1/2 of 1 plus cosine 2u. So again, there is a reduction of the exponent or the power from 2 to 1, but make sure that you double the angle u. It becomes 2u. We now work on the integral of sine squared 3 theta cosine squared 3 theta d theta. So you can see that both powers are positive even integers. So we shall apply the identities for sine squared and cosine squared. Sine squared is 1/2 the quantity 1 minus cosine of twice the angle. 3 theta will become 6 theta. For cosine squared 3 theta, the identity is 1/2 1 plus cosine of twice the angle. So again, it becomes 6 theta d theta. 1/2 times 1/2 is brought outside, equivalent to 1/4. The integral of, what do we see here? 1 minus cosine and 1 plus cosine. It is a special product. It's similar to a minus b multiplied to a plus b which yields a squared minus b squared. So 1 minus cosine times 1 plus cosine is 1 minus cosine squared 6 theta d theta. We separate this into two integrals. 1/4 d theta minus 1/4 cosine raised to 2. No? Cosine squared 6 theta d theta. The first one is the integral of d theta, which of course is equal to theta. Then minus 1/4. And what do we see here? We see cosine raised to the power of 2, which is even. So it falls under case 2. And for case 2, we apply the identity for cosine squared, which is 1/2 of 1 plus cosine of twice the angle, that is 12 theta d theta. We continue. 1/4 theta minus 1/4 times 1/2 is 1/8. We integrate d theta, which is theta. How about cosine of 12 theta d theta? The integral of cosine is sine of 12 theta. And the differential of 12 theta is 12 d theta. So we know that it lacks the constant 12, and the reciprocal will figure out in the answer. So 1/12 plus c. We can combine 1/4 theta and negative 1/8 theta. So 1/4 minus 1/8 is 1/8 theta, or theta over 8, minus 1/8 times 1 over 12 is 1 over 96. 8 times 12 is 96. Sine of 12 theta plus c. That is the integral for sine squared 3 theta cosine squared 3 theta d theta. Let us now try the integral of sine squared c cosine to the 4th c dc. So both powers of sine and cosine are positive even integers. We apply the identities. For sine squared is 1/2 quantity 1 minus cosine of twice the angle z, or 2z. For cosine raised to 4, we know that that is equivalent to cosine squared c raised to 2. And for cosine squared c, that is 1/2 1 plus cosine of 2 times the angle c. Everything squared times dz. So let us get rid of the constants inside the integral. 1/2 times 1/2 squared is 1 over 8. Then 1 minus cosine of 2z, 1 plus cosine 2z quantity squared is c. So we will expand 1 plus cosine 2z quantity squared into 1 plus 2 cosine 2c plus cosine squared 2c, and multiply these two. We multiply these to 1 minus cosine 2c. And what do we get? We shall be getting 1 plus cosine 2c minus cosine squared 2c minus cosine cubed 2c dc. Okay? So, expand 1 plus cosine 2c quantity squared and multiply it to 1 minus cosine 2c, and this is what you should get. we can split this into 4 integrals, no? Or we can proceed by integrating dz, which is equal to z, right? The integral of dc is z. How about the integral of cosine 2c dz? The integral of cosine is sine. So plus sine of 2c. But you need to check your u. Your u is 2c. So that will introduce 1/2 in the answer. How about cosine squared? For cosine squared, it falls under case 2. So we cannot integrate it yet. Now we apply the identity for cosine squared, which is 1/2 integral of 1 plus cosine of twice the angle 2c, it becomes 4c dc. That is for cosine squared. Then minus the integral of cosine cube. So in this case, cosine cube will fall under case 1. No? This falls under case 1. Cosine squared falls under case 2. So cosine cube is written as cosine squared 2c times cosine 2c dz. Okay? So 1/8 quantity z plus 1/2 sine of 2z minus 1/2. Let us integrate dz, which is equal to z. And cosine 4c dc is 1/4 sine of 4z. The integral of cosine is sine. But because of 4z, the differential is for dc, 1/4 will figure out in our answer there. Minus the integral of cosine squared becomes 1 minus sine squared. Remember, we are applying here the rule of case 1. So cosine squared becomes 1 minus sine squared 2c times cosine 2c dz. So let me erase that. Cosine 2c dz. So 1/8 z. 1/2, no, z minus 1/2 of c. C minus 1/2 of c will give us 1/2 z. Okay? Plus 1/2 of sine 2z minus 1/2 times 1/4 is 1/8 sine of 4c minus, we have here the integral of cosine of 2c dc minus minus, so that will be plus the integral of sine squared 2c cosine of 2c dc. Okay? So we continue. 1/8 1/2 c plus 1/2 sine of 2c minus 1/8 sine of 4c minus the integral of cosine 2c is sine 2c, but because of 2c we shall write 1/2 plus, for the last integral, we will be using here the power formula where u is sine 2c and du is 2 cosine 2c dc. So it lacks 2, we multiply by 1/2. So that will be 1/2. Sine squared will become sine cubed 2c all over 3 plus c. And note that we can cancel 1/2 sine c and negative 1/2 sine c. Okay? So that will reduce to 1/8, 1/2 c minus 1/8 of sine 4c plus 1/2 times 1/3 is 1 over 6 sine cube 2c plus c. That is our final answer. Okay, you now try working on the following exercises: the integral of sine cube t, square root of cosine t dt, and the integral of sine squared 2x cosine x dx. And we'll check your answers later. For the second integral, the hint here is you apply the identity sine 2 theta equal to 2 sine theta cosine theta. Okay? And, okay. So, in a few minutes, we will check your answer.